Hi everyone, my name is Zina Rockowitz. I work at NYU Langone's Alzheimer's Disease Research Center. Thank you everyone for coming to learn and hone on using artificial intelligence for early detection of Alzheimer's disease and related dementias. Please note that participants are muted upon entry. Following the presentation, you can unmute yourself to ask questions. If you prefer, you can also type questions in the chat box as we go. And we'll have a survey at the end in which helps with our programming. So if you could fill that out at the end, we thank you so much. Our presenter is Dr. Razavian. She is an assistant professor in the Departments of Population Health and Radiology and is a member of NYU Langone Center for Healthcare Innovation and Delivery Sciences and its Predictive Analytics Unit. Her lab focuses on various development and applications of advanced machine learning and artificial intelligence for medicine with a clinical translation outlook. Her lab works with medical images, clinical notes, and electronic health records. Before joining NYU Langone, she was a postdoc at the NYU Current Institute of Mathematical Sciences, and she received her PhD Carnegie Mellon University in Computational Biology Group. All right, take it away.
Thank you so much for the introduction, and it's really a pleasure to be here with you guys today. Thanks for joining this seminar. So as Zena presented and kindly introduced me, so I am a technically trained faculty here at NYU, meaning that I am expert in my expertise is in machine learning and AI. And I have been now, it's been 7 years that I have been involved in the Alzheimer's Disease Research Center activities to try to improve several tasks related to Alzheimer's disease, leveraging advanced AI methods. And it's really a pleasure to give you some of the summary of what we are up to. So we all probably know that early detection in Alzheimer's disease and related dementia is key. Right now, basically most of the clinical trials recruit and address mild to moderate ADRD. I'm going to call Alzheimer's disease and related dementias ADRD. So there are now some FDA-approved therapies that actually have Medicare coverage, which are only applicable at early stages of impairment. So it becomes even much more significant that we actually detect this condition early. And so there's also some trials that actually tell us that cardiovascular intervention actually statistically significantly lowers the risk of conversion to mild cognitive impairment or ADRD, meaning that really if somebody is at risk, if we know that and if we address these things, there's definitely a lot of potential to improve cognitive health of all of us. And there's these are really large trials that have successfully completed. Sprint Mind is a famous large government-funded trial that was very interesting and very promising. Another one is called Preventable. It's addressing cholesterol control. It's still on the way, but definitely Sprint Mind is it has already concluded that hypertension control is impacting progression and basically preserving healthy cognitive status. Okay, so these are all things that one can do if we can detect the Alzheimer's disease and dementia and mild cognitive impairment early. There's also a lot of benefits, as you may very well know. You're all interested, I know, in this condition. That's why you're showing up, and you're probably quite better than me educated in all the value in various resources that are out there, including caregiver support, financial planning, etc., that could be delivered. And of course, not needless to say that we do need better enrollment for clinical trials. So right now, the clinical trials are quite diverse, but we do need some more diversity on them. And so trying to identify early detection for different subpopulations that tend to not benefit from resources would be improving the diversity of clinical trials. So all of these are reasons that this early detection is key. And since 7 years ago, before there was any FDA-approved therapy with or without controversies, I had focused on early detection, and that is kind of what we will continue to focus, and it has just increased in its significance. Now, in terms of part of the problem that I have seen, it has been reported in the literature, etc., is that there's disparities in early diagnosis of this condition. There are already big gaps, and even among those gaps are even higher for racial and socioeconomically minority subpopulations. Two-thirds of the ADRD patients at the moment are women. There's a lot of let's say racial differences. If you observe the prevalence, that's one thing. And then when there is some condition, Black and Hispanic patients have been documented to not actually go to neurologists. They will not have as much access in their neighborhood, in their areas to go and receive care from neurologists and to get proper diagnosis, etc. And in fact, in that paper, lower education, lower income, being uninsured, all of those reduces access to neurologists. And you know what? These are the risk factors also for various conditions that correlate with dementia. Over here, you can see that over our life, like there are some very rough, very high level conditions that may influence the risk of cognitive impairment. And all of these actually correlate with the stress in life, you know, the socioeconomic status, and those also at the moment correlate with racial conditions, with gender, etc. So all of these disparities that we see actually are highly related to, in fact, those populations who would most benefit from early identification. And as I mentioned, at the moment, most of the trials are primarily white, primarily educated groups, which is important group, obviously, but also it could be better. We all agree on that one. So our goal in our team and a lot of collaborations that I have formed over these years is to focus on bringing this early detection to the clinic. Okay, at the moment, most of these patients I'm talking about who are high risk, they're only seeing their primary care or family medicine for other things, not necessarily for cognitive things. They might have hypertension, they might have, you know, cholesterol issues, heart problems, etc. The cognitive health is not at the top of the mind of those PCPs. Those PCPs are busy. So how do you solve this challenge, right? And one way, easy way would be, oh, train more neurologists and, you know, put them, you know, at offices everywhere, but that's not very practical. And at the same time, we are all aware of, you probably already know, and you have heard about things like ChatGPT. Those kind of technologies on AI are already driving our society. They're changing it. So can they actually also help us deliver high quality care across all spectrums of the clinic, and you know, still elevate the level of care that everybody gets and address this early detection challenge, especially with the focus to all subpopulations, you know, rich and poor and all sorts of dimensions and demographics. So there is a great opportunity in reducing this disparity in early detection. And I will show you two elements, two directions that we start to tackle this problem. There are many dimensions. We have started with two dimensions. One is looking at something we call electronic health records, and another one is looking at clinical MRIs to build and validate models. And we are very rigorous in terms of our scientific approach. We make sure these models generalize, etc. We work on integrating them into actual clinical workflows. A lot of exciting things that we are doing, and I'm happy to tell you a little bit throughout this talk. So I will give you throughout the rest of this talk a little bit background on just very zoomed out version of like the story of where we are with AI, a bit of those methods, and a little bit of intuition what AI actually means. And then we jump into a little bit what we're talking about when we talk about electronic health records. What does these things anyway? And then I dive into this specific two dimensions that I told you, MRI data for early detection and the electronic health records, which we can write EHR data that would refer to electronic health records. I'll tell you all of this, and then we will wrap up. Okay, so before we start, so I guess you are all aware of it. There's AI, there's machine learning, there's deep learning. What are these like differences? Honestly, it's a very like fluid spectrum is kind of hard to cut off, but if you think about it, AI is a bit more general terminology. Anything that kind of shows intelligent behavior, it's called AI. Machine learning is one way to achieve AI by exposing computers to a lot of data that has been potential, basically having the computer mimic a human by showing a lot of human actions with the input and output, and they will like the computer, the algorithms will learn this I guess transition from input to output. That's called machine learning. And then deep learning is one specific type of machine learning. There are many types. Deep learning is a stronger set of methods that are also more data hungry, but recently with all is, are all around us, everything is digital. We have our phones, everybody's taking photos, everybody's talking online, like texts and images are pouring everywhere. So like we are in a data heavy world right now, and deep learning is right now the front runner of all of these approaches. So I guess just like a minute, just to give you an intuitive example, what does deep learning actually do behind the scene? Okay, and there's something called convolutional neural network that kind of everybody does when they deal with images. Okay, let me show you like what kind of at least the gist of it. Imagine that the task was not about ADRD. Let's imagine that we are looking at the person's retina. And then the task that the machine has to do is identify if there's retinopathy in here or not, okay? Like if there's any problems in the retina images. Normally, what happens is images are like kind of complex, and it becomes easier if we look at certain transformation of this image. Right now, this image kind of has the edges kind of pulled out, and like it's a little bit more highlighting some regions that might be interesting, maybe, okay? And then how do people in our world achieve it? They kind of like mathematically, like there is this little kind of a bunch of values here that actually kind of scroll over the image. And if they scroll over it, that task is called convolution. We don't care what exactly is the part of it. It will transform this image, okay? The whole, before this whole deep learning revitalization that started in 2013-ish, like 10 years ago. Okay, before this, computer vision people mostly were like basically researchers on the AI side of things, were mostly manually designing this little box, okay? And it was suboptimal. And then the whole value of deep learning is, hey, don't manually design them, just learn them, let the models automatically infer them throughout the process of like providing it with input and output, just like build the machinery to actually infer this. So that was the birth of convolutional neural network. That is kind of one example of deep learning. That's the key difference of maybe machine learning and deep learning. In deep learning, you can directly learn these. You don't have to manually specify all of these things. And then this model, this model is like, it was invented in 1980 something, but then it was re-implemented in 2012, I guess, 2013-ish. That's when it was published, 2013. And it can be applied to a lot of things, including brain MRIs, including other type of imaging, to try to kind of solve our problem. Basically, try to, let's say, take an input, let's say an image, and then predict an outcome. Now, that was 2013. This model was called AlexNet because a dude who actually implemented it successfully for the first time and started this whole new revolution, his name was Alex. And then where we are now is 2024, and there's like a whole lot of models that have kind of opened up after it. You may recognize ChatGPT, maybe you have heard about it, right? It's this dialogue system that's really intelligent, and it can actually hold really interesting conversations with us, with users. I wrote a poetry book for my 2-year-old daughter, actually. I'm not a poet, but I asked ChatGPT, say, write a poem about, the style of Dr. Seuss. And we actually did a pretty good job. And we self-published it, and my daughter loves the book, right? So this is where we are now. This was the starting point in 10 years. The yellow lines kind of show you some trends. Maybe some of you guys have heard about some of these models. Maybe some of you haven't. It doesn't matter. It's not the focus of this talk. But in computer vision communities, people, and these are yellow boxes. Those are some developments that are getting better and better. Then in the blue boxes, it's language things, text things that evolved. And then in the red part is like generating things about generating nice images and cool things. They all started to evolve, and at some point they kind of started to actually follow similar methodologies. Up until 2017, we were in one era of machine learning, which is kind of it's called supervised learning. Afterwards, we entered another era, which is like a gear shift. Okay, the models just got like billion scale, and like suddenly the community was no longer afraid of smaller models. These models are massive. They're called foundation models at this point, and they became a lot more performant. Okay, now we don't need to necessarily talk about these two like eras, but a lot of problems in healthcare that we have always dealt with, including COVID, actually, a lot of unknown things that AI could have helped us during COVID. The right answer for that lies in this new set of approaches, which we call self-supervised learning. Basically, the gist of it is we no longer need massive labeled data sets to train our models. We can just use unlabeled data, basically just images alone without the doctor's diagnosis, combined with it, would be enough to train most of the model. And then you just need a tiny little bit of data sets, which is typically what happens, what is available in healthcare to kind of fine tune those big, nicely trained models. So like that approach, this approach is just really much more suitable for interesting problems that we're interested in. And that's kind of what we do. Okay, now a little bit of giving you context. So all this ChatGPT setup that we talked about, right? You may have heard about it. Those are all trained by Google and Facebook. And you would think, okay, those companies are like, they just have so much more data. Guess what? No, in healthcare, we actually have equivalent amounts of data. And teams like my team actually sits on this data. And then they're like, look, we can actually build similar high quality diagnostic prognostic tools from the data that's already in electronic health record system. Every time you go to the doctor and they turn their back to you and they start typing, at the very least, a good thing about that is that that data actually gets stored in the databases. If somebody undergoes an imaging, that imaging is there. All their history is there, like 5 years ago, what happened, 2 years later, what happened. All of this data is a wealth of information that can be used. So giving you a little bit of just a little insight into what is currently at NYU Langone's database. It's just sitting completely untapped, These are like, red is how many patients have received certain service across some conditions. Let me give you some examples. So let's say cancers, okay? 500,000 patients have received cancer at NYU Langone. And all of those treatments, prior signs of cancer, during the diagnosis process, these data can be, compared to existing studies, this is 100 times larger or 1,000 times larger. So it can fuel a lot more advanced models. And that is kind of where I see the future, more stronger models, more advanced models, but they tend to need data. But the data is there. So there's a lot of opportunities there. And that really excites me. One challenge, that's my job to deal with, is like this data is so diverse. And so there are so many different ways, like imaging and radiology gives you these kind of things, like if it's a heart, if it's a breast, if it's a brain, how does one even work with all of this data? And then something called electronic health record is like lab results over time, medications, and then disease diagnosis. They're like discrete little like signals that just like over random time points kind of accumulate. How do we handle all of this? And then we have text that's usually like, you think that doctor's handwriting is ineligible. That's not the problem. The problem is the way they record things, even if they type, it's quite ineligible. So all of this, and then histopathology images, like these are complexities that it's our job to deal with. But at the end of the day, this part would deal with that. Don't worry, you don't have to worry about it. It's that we are interested in finding signals in, let's say, patients' prior timeline, let's say up to now, looking at anything that's available and try to estimate, let's say if you're interested in early detection tasks, trying to estimate 2 years from now, 1 year from now, does this patient has a risk, or 5 years from now, do they have a risk for certain conditions? And the rest would be the machinery and the methods that we develop, which is not really the focus of this paper, this talk. Okay, so I will, if you're interested, ask me questions, but I will not like bore you with the actual details of it. So I'll tell you the whole this talk is around, I guess, 2 sets of studies that have been funded by National Institute of Aging and also NIH, which I will list here, and I lead these 2 studies. One of them is about more and more advanced AI methods. It's an AI proposal, okay? It's a method development. The other one is actually about rolling out some existing AI model that we have developed into clinical settings and seeing, you know, what, and hearing from patients and doctors, what do they want to see from these models, and actually trying to see if these models do eventually make a difference in terms of early detection, especially for those underrepresented patients. So with all that said, and you're welcome to stop me at any time. If you have questions, I'm more than happy to, you know, like pause and explain more. I will now let's kind of dive a little bit into like 2 of the examples of what we kind of promised to do, which is one was looking at the person's MRI image. Can we identify signs of MCI or ADRD? The other one is looking at electronic health records of the patient, which is like without even asking the patient for imaging or anything. And the data kind of just lives already. It's there. If they come in for their cardiovascular thing, but they have they have risk for cognitive impairment that their doctor just haven't had a chance to think about it. Can we estimate the risk within a short future time frame and help the doctor prioritize certain things to address during, let's say, annual wellness visit? At least ask about it from the patient, right? So that would be electronic health records. So let's start with the MRI half of the, I guess, studies. So this is, if you are interested, read our paper. It's generalized deep learning model for early Alzheimer's disease detection from structural MRI. Okay, it's a published paper, and it was a really fun collaboration and really promising collaboration that led to quite a lot of the awards that you see, the funding awards that you see are basically like the after effects of this study. So in general, why do we care about MRI? So at the moment, as you are well aware, people use PET imaging, right, with beta amyloid and tau tracers to try to identify if somebody could benefit from the therapies. That's one thing. And then also, you know, we also, that's how we diagnose ADRD. Mostly AD version of ADRD is good for beta amyloid and also tau. So there are issues with this. So one issue is they're expensive. Another issue is they're kind of invasive. They require some injection of apologies, injection of these tracers. And then so that if they're expensive, like who's going to pay for it? Insurances don't always cover it. And there are even, like, let's say if we talk about tau, they're not even standardized yet. It's like really a research grade tool at the moment and not clinically accessible. Now, let's say far away in some neighborhoods, you know, in Queens or, you know, Brooklyn, where they don't even have a lot of PET, you know, neurologists with access to PET imaging, let alone specific types of tau tracers. How would we actually scale early diagnosis across the entire US and across the entire world, right? So that's a big question. Now, one thing that we know is that our brain, actually, some structural changes start to happen. And in the extreme case, hippocampus, for example, starts to shrink and like the gray matter starts to kind of thin. But those are later stages. So what we thought and what we think and what we showed is that if you use AI, it's more capable than just, you know, our human eyes, which is like usually sensitive to big changes. AI can detect smaller changes. So that was a question that we were interested in. Structural MRIs are much cheaper. They're a lot less invasive. They don't require much of any injection of anything. They're faster. They're 5 minute kind of in and out kind of things rather than, several of a day kind of imaging. And they are cheaper and more accessible. In fact, like in parallel, while we are talking about this, some other interesting development in AI and imaging has developed these portable scanners that are like, they don't even need a room. Normally right now, even MRIs are like kind of big, but like there's so much progress in the MRI field right now, the structural MRI part of things. So there's a lot of opportunity, and what has existed out there on these, like, I guess, on technologies that could read these MRIs were just not sufficient. Like they were very traditional approaches, kind of rough. They wouldn't be able to detect early signs, but early signs are the part that we care about. So anyway, after all this, the question that we're interested in is, can we use AI, deep learning specifically, on 3D volumes of MRI, structural MRI, I'll show you what that looks like, to better identify MCI and ADRD. Okay, that's kind of our goal for early identification. And then the next questions are, can we integrate them into clinical settings and measure their impact? And eventually the end goal is, at the end of the day, does it change patient outcomes, right? So all of these are questions that we are interested in. We started that paper, that study, with the data that you guys are actually providing throughout these initiatives. So NYU is part of ADRC, which actually nationally pulls all of this data, and you know it very well. So what we used was ADNI and NAC data sets. They are both benefiting from your participations, and they have accumulated really valuable sources of data. So we primarily actually trained our model on ADNI data, but usually when you have deep learning models, it's important to evaluate them on external data sets, meaning that on domains where the thing wasn't trained on, because usually deep learning is pretty good at answering you correctly on its own training data, but it doesn't necessarily mean that it can work well on external data. And external data meaning new patients, new settings, new centers in Manhattan opening up. Is the model still going to be good on those? So those are the questions that one has to be critical about with deep learning, and that's kind of the way we work. We are very rigorous in terms of our science. So we used a very large data set, NAC, which NYU also contributes to, like you guys also probably contribute to, and as a validation data set. Okay, we assume that, okay, what about this? What if this data wouldn't even be part of the training data? How well do we perform on that one? So the data sets that we use had different level of individuals, like 600 in ADNI and then 1,500 in the NAC. When we published this study, and that was like 2019, 2020, where we actually completed a lot of this, the data sets were smaller. Now we have more data sets available, so that's good. NAC has benefit that it's a little bit more realistic clinically, because ADNI is a lot more exclusive, I would say. They exclude patients who have cardiovascular problems. They exclude patients who have diabetes problems, like severe problems. And you know what? I mean, these are high-risk patients. So in NAC, that exclusion doesn't happen. So if you think about real-world clinic, I actually like NAC a little bit better because it actually reflects diverse ADRD settings. And to be honest, like the subtyping at the moment is one should take it with a grain of salt anyway. Like even ADNI, which claims to be only Alzheimer's disease, our study have shown that patients who are diagnosed with only Alzheimer's disease, sometimes they also have Lewy body pathologies in there. In fact, studies 2% of them have, like a third of them have other pathologies, including like Lewy body tangles, etc., in the brain. So it probably would be a good idea to address ADRD as a whole rather than think that we are good at separating AD from Lewy body, from all different mixed Lewy body, etc., right? So I like NAC anyway. So we use all of these for our training and evaluation. Basically, ADNI was our training data, and NAC was our external validation data. Never touched during the training. We basically thought, okay, What if NAC is a new center? And then how does the model perform on that? This is just a general statistics or characteristics table of the data set. They are relatively like balanced in many ways. So the modeling thing, it doesn't matter, you know, I'm not going to dig into it. We developed there is some non-trivial things that we had to do to make sure our models can read an MRI and identify whether or not somebody is cognitively normal, has mild cognitive impairment, or is at the stage of Alzheimer's disease. This is our results. Normally, like you want to achieve higher is better. And stage early detection usually means being able to identify if somebody has cognitively normal versus MCI versus the rest, basically. So this is actually the key line that we are interested in. And the results were quite promising. One can detect cognitively normal, let's say in ADNI, which is our training data set. It's not as, we still had held up validation, but it's still not as valuable as learning about NAC. We are talking about 88%, and then on NAC data, which is completely unseen, we're talking about 85% accuracy in terms of some measure we call area under ROC curve, okay? In terms of identifying MCI or ADRD stages, okay? Which has really exciting implications. Now, another way to evaluate it, this one is called ROC curve. This one is a little bit like sensitivity specificity. There's another curve that we also look at, which is precision recall, meaning at certain, at certain sensitivity, what is actually the precision of this model? If we start to alert the PCP that, hey, you know, you may want to think about a conversation about cognitive health for this patient. If we alert, you know, 10 patients, how many of them are going to be positive? This is the y-axis here tells us like how many of them are going to be like correct. Okay, and that's called precision. That's actually probably more actionable than everything else, because like if it's not very accurate, the doctors would be disappointed, the patients would be like, what are you talking about, right? So you kind of want to identify the right population who would benefit from these kind of conversations. So when I saw this thing in that paper, you know, when we saw the results on NAC, for example, where performance like had pretty good sensitivity, like if we want to capture half of the entire population who have any impairment, let's say we start with half, okay? We are correct 4 out of 5 times, basically 8 out of 10 times we are correct. That's actually pretty good correction, you know, rate for some scan that's like MRI, that's cheap and accessible and can be, you know, used all across the New York, bigger New York area, all the neighborhoods, and also across the US and beyond that. That was when I was like, okay, we need to think about how to go to the clinic. Okay, so that was a really promising result. We also compared to something you may have heard about, it's called FreeSurfer. It's a traditional tool, okay? It's statistical, older style of models. It's not AI, it's like traditional approaches. And the performances that we saw were just a lot better with deep learning compared to those traditional approaches. So really deep learning is the way to go. Another very striking finding was that even when the model was considered to be incorrect, meaning that if the patient was predicted as AD, but they were actually not really at the stage of Alzheimer's disease, they were more at the stage of mild cognitive impairment. If you track their progression, let's look at this one, okay? You track their progression across time, you will see that those cases where the model predicted them as AD actually did progress faster. So the model saw something in there that actually maybe the doctor didn't see, but eventually it happened. So this model is actually, you know, quite an interesting model. We're not obviously done yet because this was done on ADNI, and I'll skip this slide. We also explored how good are we on male and female, high and low education, people with genetic mutation, etc. And the performances were good. And we compared it with this like FreeSurfer, like the old style statistical approaches. For most of these cases, deep learning was better. I won't spend too much time on this, but I'm happy to dig into it later. And then these models also, there's some questions like which new regions are they looking at that we're missing out? So first of all, they look at different types of patterns in the existing areas, like maybe shrinking at the top of the hippocampus versus the bottom makes a difference, or this kind of thinning of the gray matter is the key, etc. So this is, I guess, the scientific side of things, where this model actually provides you with some hypothesis. Hey, I see these other things, that are predictive. So that's also another good side of these models. So this said, when I saw those curves, I was like, that was like 2-3 years ago. It's like, okay, let's start to think how can one actually benefit patients from these tools while we still continue. 80% is pretty good to start with. We will still continue, but we don't need to wait 10 years to get to 90% to actually do anything. Let's see what we can do with that 80% while we still push the other performances. So what we need to do to actually answer that question is several steps, actually. And we started those steps. So first of all, we start to pull and look at clinical grade data. So you are all probably aware, NYU Barlow Center, you probably have, good information about Barlow Center, right? So Barlow Center is not just about participants of the study, it's actually caring for patients. So if you look at de-identified data from patients who had a visit from one of these 10 neurologists over the past several years, 10 specialist neurologists who have been at Barlow. First of all, that sample is quite large, 5,000 patients. It's bigger than NAC, it's bigger than ADNI, okay? And then of those, 3,100 had been diagnosed with ADRD when they were over age of 65 and diagnosed. That's actually a really rich new data set that we can do. And as part of moving to the clinic, it's important that we actually evaluate our models before involving any patients directly and wasting doctors and patients' time. We can do our homework and actually see how good these models would have been. Would they be able to tell the level of neurologist diagnosis based on these MRI scans? So that's what we started with. So I would look at the middle one, which is like the model that we just talked about. You basically just recalibrated it a little bit to the clinical level because the distributions are a little bit different, but like in terms of the prevalences. Okay, but you don't need to train the actual model at all. It's just the last layer. A recalibration actually achieves pretty good performance still, like 85% performance in early detection at the clinical level. The differences in the clinical level versus, ADNI and NAC kind of like research grade, high quality data is in the clinic, those scans that they're applied, they're not always standardized at the same level at, research levels. So it has always been a challenge, especially with more traditional models, that the models wouldn't really work the moment the scan becomes a little bit more blurry or a little bit, instead of being this dimension, like a little bit changing the dimension, it will break the system. But the good news is that deep learning kind of likes behaves like how doctors, how humans, behave. Like if you know what a dog looks like, you won't forget about it if the dog, it's a new dog, or if it's night or day or something like this. It's the same thing with MRIs. If the pattern is learned, then it's okay if it's a little bit shifted. So deep learning doesn't break same way as traditional rigid models. And we saw that performance that was really promising. And so I'm going to pause here for a second. What we have seen, where we are right now, is that we actually have seen that the performances are promising in the clinical setting. In the research setting, we already published it. In the clinical setting, we are finishing up the manuscript to actually publish it. And then it really opens up a lot of cool potential for identifying patients who normally wouldn't really have access to these, more advanced imaging kind of diagnostic processes offered by neurologists. What we have as an ongoing work is that we still want to improve that 85%. Okay, don't mistake that. Like that still can be pushed back to 99% accuracy or 100%. But the main other thing is we're planning to see how can we integrate it into the clinical workflow of the radiologists and people who actually read these scans and start to assess the impact of it. And so that's where we are with the MRI. It's very diverse set of conversations we always have on a weekly basis. We have with several colleagues and several team members who are working on this. I'm very proud to be part of it and lead some of these studies. Now, let me quickly tell you a little bit about the EHR side of things, and then I will spend less time on this side. But what is electronic health records? I kind of told you, like every time you go to, to doctor, even if it's not about specifically brain imaging, if it's about hypertension or just normal, annual wellness visits, hey, how are you doing? Let's just do a blood panel just to make sure everything is good. All of those data gets poured into a system behind the thing in the computer, and that data just sits there, okay? And those data can just be really high dimensional. It has medication things, and not everybody has the same medication, but it has the footprint of all of these things are there. If we want to use it, that we can potentially think about how we can use it. So that if somebody has diagnosis, it will be recorded. If somebody has certain lab values, and imaging is actually part of this whole system. If there are some procedures, etc. And even like if one think about like a little bit more advanced things, like activities, if somebody actually wears a Fitbit and they're interested, they can actually plug in their data. I don't think, to be honest, these parts are not right now clinically there yet. Primarily, these top parts are the parts that are captured, but we will get there. I'm pretty sure in the 5 to 10 years, we're talking a little bit differently in terms of what information is available. Now, the challenge is this information that's actually really high dimensional. We're talking about 500,000 different variables at the minimum that could be modeled. And these different variables kind of connect with each other. They're related. Okay. Diseases, at the moment, there are like 80,000 possible diseases that could be documented. 80,000 different ways one can document, all diverse possible diseases that one can have. It's very high dimensional. There are over 70,000 possible labs that could be administered at L's clinic. Okay, these are really high dimensional. 90,000 medications, 40,000 potential procedures that could happen. So this high dimensional data is this beast that, as a methods person, we have to deal with to try to use, like, let's say, part of the data and then try to predict 2 years into the future certain outcomes. It's both a very wonderful blessing and also a curse. And so one thing that kind of helps us, but also creates some challenge for us, is that these variables have connections between each other. For example, if somebody has diabetes, it's likely there are some guesses that we could potentially, make, or at least certain things become more likely. Okay, it's not 100%, but they might be more likely. So they might have some obesity signs, or like at least, not, a normal weight level. It's more likely. It doesn't mean that they for sure have it. It more likely correlates later with hypertension, hyperlipidemia, and actually diabetes over time progresses to kidney problems, etc. So we may know some things. So this is a property, I guess, of EHR data that could help us later. If we have missing data in one of them, can we kind of infer the other ones? In fact, that's kind of what we want to do about MCI and dementia. Like, what other factors are there around the patients who have MCI or dementia, which was there in their records over time? What patterns that was there that would differentiate them from those who didn't transition, right? So these are helpful, and also, I mean, methodologically, we have to work with them. Like, we have like this 500,000 big tangle of relationships between these variables that the computer's models have to learn to be able to actually do the work that they're supposed to do. So we specifically define our task. I'll kind of tell you a little bit about it, but not really the details. For patients over 65 who do not have any diagnosis of MCI or dementia, who will likely be diagnosed with MCI or ADRD in the next 3-year time frame. Okay, we kind of, for now, actually our data allows us certain lengths of prediction. Every year that data length grows. Ideally, I would like to have more heads-up time so that the interventions, cardiovascular intervention, etc., could be more helpful. But at the moment, our data length, the high-quality data we have, is from 2013-ish to 2024 now, right? It's like 10 years of data. We can't separate these prediction windows too much yet, but we will do that. Anyway, for now, we're looking at short-term time frames for prediction, looking at the patient's data up to a certain time point. It's machine learning's job. You don't have to worry about it. I will tell you, and if you're interested, I'll tell you more about it. It's a machine learning's job to predict whether or not the patient is likely to have MCR or ADRD in the next, let's say, 3 years. Okay. And that's kind of the way we've formulated. And the fact that these variables are 500,000, it's our problem. Okay. That's an AI designer's problem. How does one work with 500,000 variables? Statistical methods no longer work in this regime. In fact, statistical methods basically fail the moment you have a lot of high correlations between your variables. And guess what? Like that's the entire EHR data is a bundle of correlations. So really old style statistical methods don't really work. This data is fully de-identified, but because it's only about diseases, like the basically trajectory of diseases, maybe lab values, trajectory of those. So we can leverage a lot of basically much bigger data sets for EHR analysis compared to our MRI study. We're talking about 300,000 patients over 65. Of those, 50,000 were diagnosed with MCI or ADRD. We are getting closer to a little bit the real distribution of high-risk patients for MCI or ADRD. If you remember in ADNI and NAG, the distributions were like maybe 50-50 or something. Now we're getting close to 60-40. It doesn't necessarily mean that, like we want to exclude certain populations, but at least we know that now we have representations from high-risk population. We are a lot more racially diverse. In fact, like we kind of know that 10% of our population is Black at the moment, 5% Asian, 50% white. The rest are either mixed races or other races, or some of them are unknown. Okay, so it's a lot more racially diverse population. It's very cool. So that was the task that we defined. We'll actually skip it to not confuse you. How do we define Alzheimer's disease and mild cognitive impairment? It's like a bunch of codes that the doctor might have documented, or a bunch of medications that, like, even if the diagnosis didn't really get documented, if they started the medication for the reasons of these conditions, then we would consider that those as cases that would, that would be the beginning of the MCI and AD trajectory, the first time we see these things. Okay, so on that note, I won't talk about the methods, but like we built advanced models, graph neural networks, like graph-based deep learning, which leverages this like tangle of relationships that I told you about to try to answer this question. The methods I will skip because it's very technical, but if you are interested, I will tell you about it. At the moment, our results, actually the basis of the next steps that I will tell you about, is quite promising. So compared to some existing models, we achieve over 10% improvement. Like the bottom lines are like the statistical models that already was quite popular and made a lot of news. This model is a lot more accurate in terms of identifying these patients. And so we call it EHR BERT. The straight lines are the top ones here are EHR BERT. The blue line is if we predict within 0 to 3 years, and the red line is if we predict within 1 to 3 years into the future of the patient. Okay, each of those have different, I guess, properties that's maybe irrelevant to this talk. I'm happy to talk about it later. But this performance that was achieved after actually the first paper, which we published in 2021. And we started an R01 with basically an award, a proposal, a funding proposal, a big one to the NIH that said, hey, we want to take this model. We will still improve it, but what we have already right now could be insightful and trying to identify, like basically fine-tune this whole clinical integration. So what we are doing is we actually are alerting PCPs of, so we picked 2 centers in Brooklyn, which had higher racial diversity, and we put these models behind the scene. Okay, we're doing it. We're in the process. That's a grant. It just started this September. What we are doing step by step is that we are putting this model behind the scene, and a random half of the providers, the PCPs in these 2 centers, are gonna be alerted about the benefit of cognitive screening if their patient is high risk and there's no record of any discussion or any kind of screening. So half of them are going to be alerted, the other half, they just do the normal activity. And what we're going to track is whether or not these patients are going to, do we make any difference in terms of basically the screening rate for these patients, potentially early diagnosis, but like our primary thing is just offering patients screening opportunity. And the second one is the cardiovascular interventions, which we know if they are done ahead of the conversion, they actually delay the progression to the disease. So that, for me, that is kind of the key part to offer this opportunity to these patients who are high risk to try to improve their cognitive trajectory, basically. Okay, so we will track these things. The actual trial will start next September, just so you know the timeline. Right now, what we are doing is, first of all, putting this model, like the mechanics of putting the model behind the scene is one part of it. The other part is we're actually having user studies, which involve patients and PCPs to ask them, what do you want to, if this technology would be available, how do you want the information to be presented to you? What do you actually prefer? Like, do you actually even want to know about the cognitive side, or do you actually only care about the cardiovascular side? Like, maybe patients don't really want to know about why my doctor is suddenly caring about my blood pressure, but like maybe it's important, or maybe they care about it. So we're asking PCPs and patients about how they want the AI basically to talk to them, like to tell them this information. And that will be this year. Like, we have already started some interviews, and then we will kind of make sure that whatever we design is according to preferences of patients and the doctors. And the model itself seems to be accurate on our evaluation. So we're quite excited about measuring its impact. So that's actually it. Risk assessment actually can happen. And the good thing about EHR as opposed to MRI is everybody has EHR. You don't actually need an imaging. In fact, a lot of these patients that we talk about who are high risk don't even go to MRI. Okay, that's a different problem. And in fact, that's why I started the studies of clinical implementation earlier with EHR, because that is a lot more accessible. And then the next step is, okay, let's imagine that we kind of have a way to identify who would benefit from a simple MRI, forget about PET. Then we kind of like fix the pipeline step by step. So these risks can nudge the PCPs and patients towards helpful intervention. That could be cardiovascular control, better cognitive screening, basically, an opportunity to detect things early and benefit from the care that's out there, including the new therapies. And then, overall earlier detection of ADRD. So that's basically the story of, I guess, a bunch of stuff we are up to. And I'm done almost. Let's just close the thought. AI is every day is growing rapidly. It's a very fun, rapidly developing technologies which will change humanity. And of course, we want to make sure that also improves healthcare outcomes. So our group is focusing on that one. We do firmly believe that clinically scalable and accessible identification of ADRD is possible, especially gearing towards underrepresented populations. And everything I told you about is just one of the steps that we can do. There are other things that is cooking, right now. The studies are kind of happening in a mild way, and they will also be possible. For example, now we have some therapies, right? So it's important to know what are the risk factors for the adverse reactions to therapies, because some existing FDA therapies do have like brain inflammation, etc. What causes that, and how can we improve that? That's like some type of extra questions that the same approaches that I told you about can also start to answer that. And also other questions which might be more relevant is like risk factors for behavioral problems in ADRD, like those could be very relevant to caretakers, etc. And also, we already know that ADRD subtype identification is a little bit difficult clinically at the moment. Can AI help us with that? And so those are really important questions that I'm excited that, eventually our group and other groups will kind of try to address. So that's all. Thank you so much for listening, and I'm happy to answer questions if you have any.